So I start our opening ceremony. Distinguished guests, scientists, students, ladies, and gentlemen, it is my great honor to chair and organize the International Symposium on Biomass Utilization in Agriculture and Forestry, BUAF 2022. Renewable biomass made from agriculture and forestry sectors is rich in chemicals having a quantity equivalent to more than 8 times of world energy consumption. We aim to convert biomass into high-quality energy and value-added products by advanced techniques in accordance with achieving the United Nations Sustainable Development Goals, or UN SDGs, by 2030. In this international symposium, we have invited 15 renowned experts selected from Belgium, Canada, Germany, Italy, Japan, Malaysia, Spain, USA, and China to share their most recent research activities in fields of chemical catalysis, green chemistry, biotechnologies, thermal engineering, and energy biotechnologies. The purpose of the forum is to promote international academic exchange and cooperation in sustainable development in renewable biomass utilization. It is my personal wish that the presentations that will be communicated today will help to inspire young scientists to work together in developing new ways to use biomass and to address many issues in energy and the resources all over the world. Thank you for your attention. Next, I would like to ask the Vice President of Nanjing Agricultural University, Professor Feng Fu, to provide some inspirational messages. Finally, I would like to invite Vice President of Chinese Academy of Sciences, Professor Tao Zhang, to open the symposium. Okay, please.
Thank you, Professor Fang. Distinguished guests, dear faculty and students, ladies and gentlemen, good morning from Nanjing. It is my great pleasure to welcome you all to the International Symposium on BUAF. First of all, on behalf of Nanjing Agricultural University, I would like to extend our sincere thanks to all international scholars and participants for joining us today, and also for your efforts to make the symposium happen. Nanjing Agricultural University is one of the founders of Agricultural University in China for education, research and extension. We just celebrate the 120th anniversary 3 years ago. The vision of NAU is to achieve as one of the best universities characterized by agriculture and life sciences in the world, addressing the urgent needs and bottlenecks in agriculture, food system, climate change, and sustainable development. Currently, NAU maintains partnership with over 170 universities and research institutes in over 50 countries and regions through the joint education programs, academic change, and collaborative research programs. With great support from our partners from both home and abroad, NAU is gaining increasing recognition for its scholarship and research. Since 2017, NAU ranks top 10 best global universities for agriculture universities, agricultural sciences by US News and World Report. NAU is also committed to contribute the UN Sustainable Development Goals, SDGs, through education, research, and extension. With an increased need for food with low impact on our earth and environment, low carbon technologies, renewable energies, and development strategies are essential for sustainable development of agriculture. In recent years, the College of Engineering of our university, especially the group led by Professor Fang, can focus on the research on biomass utilization and with multidisciplinary research. That is also the purpose of organizing the symposium here today. Together, scholars worldwide and share their most recent research activities on biomass energy, bio-based materials, chemicals, bioactive compounds, and etc. And also global impact. Through this symposium, we wish to build networks, facilitate communications, and most importantly, to enhance our understanding of where we are and what we are going to do in the near future to facilitate the scientific and technological development of biomass, both in agriculture and forestry resources. The COVID-19 pandemic just showed us how interconnected our world is, and also at the same time, it is showed us how important international cooperation to address pressing challenges facing mankind. I'm glad to see worldwide scholars from partner institutions, including Belgium, Canada, Germany, Italy, Japan, Malaysia, USA, Spain, and China contribute to this symposium. And I'm confident that through our joint efforts, we can strengthen our connectivity, expand our networks, and facilitate cross-border cooperation in the area of renewable biomass resources. Finally, I thank our partners and AU colleagues for your coordination and organizing this symposium. I thank all our experts for your participation and contribution to this symposium. We look forward to meeting all of you in person in the near future. Wish the symposium a great success and wish all of you happy and healthy. Thank you very much.
Next, Professor Tao Zhang to open the symposium. Please, Professor Zhang.
Good morning. Good afternoon. Good evening. All ladies and gentlemen, all the friends. I declare the International Symposium on Biomass Utilization in Agriculture and Forestry to open.
Thank you very much. And in this morning, we will have 4 lectures. And the first speaker is Professor Janusz Kocinski from Lakehead University, Canada. Janusz, please.
Thank you very much. I will share screen in a moment. So first of all, Professor Fang, thank you for inviting me to be a speaker at this symposium, and congratulations to you on becoming the fellow of the Canadian Academy of Engineering recently. It's a prestigious appointment, so once again, well done. I should also comment on my visit at NAU not long ago. So Professor Hu, you have a terrific university and a beautiful campus, and I was delighted to spend some time and enjoy great hospitality of colleagues at your university. Thank you so very much once again. Now, I was asked to speak about some aspects of what we're doing with regards to some exotic phenomena in a variety of supercritical water systems. But perhaps before I begin, I just wanted to reflect a little bit, because it's the first presentation at the symposium, and we do have young people spending time together with us today. And I'm certain that when each of us, when we look back at our lives, there is always something that was a breakthrough that allowed us to look at ourselves or what we do or who we work with in a very different way. Now, in my case, it was the opportunity to go to space, well, almost to space, on a zero gravity parabolic flight where you go up at around up to 15 gravity forces. You can't even blink an eye, and then when you reach the altitude, in our case it was around 38 kilometers, then above the earth, the engines are switched off and you falling down, of course, together with the aircraft, and since your weight of your body is much lighter than the weight of the aircraft, you're weightless. We did it 28 times, so you can imagine that your stomach is trying to get out of your mouth or the other way. It's also called a vomit comet. But I mentioned this because when you're up there and you see the curvature of the earth, you see how small we are. It prompts you to think about what you want to do in life, especially in your academic life, in a very different way. Well, if you don't do that, and if you're in Toronto, I'll be happy to invite you to the much smaller altitude to go on a skywalk at the Toronto Tower. It's another very interesting experience. You're just attached to a rope, the highest point in Toronto. There is nothing that you can hold on, and then again, you're forcing yourself to think in a different way. Now, what happened to me and my colleagues, we started thinking about what is the meaning of the modern university? What are the borders, if there are any, with regards to research? And if so, what are the frontiers that we wanted to tackle? And then it forces you also to understand the entire system. At least that's how it is from our Canadian perspective. What are the main forces of change in the university research and education? And there's a few that I wanted to mention because I know that some colleagues will be commenting today. So one is indeed the societal priorities are different. Our society expects us in academia to deliver something that is really tangible. And we are doing that work job quite well. And it is great to see a symposium like today's conversation, that we do have a platform where we can collaborate in a very effective way. A good example is my own collaboration with Professor Funk. I think we started together maybe around 20 years ago or so at McGill University, and we still continue doing so. There is also significant disruption in the market, in academia, that is going to be linked with how we are going to redefine ourselves after the pandemic, and then how we will be able to link it with the principles and facets of the fourth industrial revolution, and how potentially a variety of policies that are being established by different governments, how they are going to affect us. So we looked at the variety of those forces, and we felt that there are certain megatrends that will define our work, including artificial intelligence and hyperconnectivity and circular economy and so on. And from the perspective of our students, what kind of skills or what kind of mindset we would like to cultivate in order for them to focus on things that are really going to define their own future, which is creativity, critical thinking, problem solving, and asking fundamental questions. Because I believe that actually the future will be less about answering questions and more about questioning answers. Now, so in short, we need truly young people that will be able to collaborate, create in a collaborative way, and consider consequences of those collaborations and their work, and importantly also to communicate complexity lucidly, because that is something that community, not just our academic community, but societies at large, that's what they expect from us, from engineers and scientists and researchers. Now, I want to share with you some of the things that we've done in considering what I mentioned previously as a platform, what we've done with regards to solutions related to clean and green energy, and especially linking it with biomass and hydrogen. Personally, I believe that hydrogen is very likely the ultimate fuel of the future, or it's one of those that will be really dominating the generation of energy, potentially generation of electricity, certainly applications in transportation and so on. Now, well, it is quite clear. I think perhaps just for our students, I may mention that why biomass is an interesting element of the entire cycle, because when it is growing, it's absorbing CO2, and when we say generate biofuel from biomass and then utilize it, then we generate CO2, and then again it's absorbed. So it's technically, it is a closed cycle. if we replace biofuel with hydrogen, as we are trying to do, then from the legal perspective, at least from the legal framework in my country here in Canada, is that we are capable of potentially removing CO2 from the atmosphere. Now, our applications, we work with a variety of systems, but I wanted to share some of our research related to hydrothermal gasification, especially the supercritical flames. And I did so because that's the subject that Professor Fang initiated quite a long time ago, more than 20 years ago, back in Canada. I believe that he was, if not the first, one of the very first people in Canada that introduced this subject in the area of research, and we had we were delighted, my research group and I, to interact with Zen throughout the years. Well, supercritical water, essentially, it's water at relatively high pressure and not a very high temperature, above 374 degrees C and around 218 atmospheres. It's a terrific medium because it's perhaps the medium that is the best solvent in that you can imagine. We tested a variety of organic materials, and it takes really just a couple of milliseconds to dissolve the organics in supercritical water. Very, very, very powerful unit. And we did a variety of applications, including very small applications such as diamond anvil cell. It's around 500 micron in diameter, 200 microns in depth. We did conduct experiments in a variety of continuous and batch flow reactors. We used a Canadian light source synchrotron in order to conduct a variety of analyses in supercritical water. It's a synchrotron is a terrific advanced analytical technique because it allows you to measure many different things on one sample. So well, essentially, just for a student, that there are electrons running around, and then there are several different beamlines. In our case, I think there are 28 of those beamlines, and you can analyze properties of your samples. You can collect radial and axial profiles. So it's a very, very powerful tool. Importantly, at least in our case, it is paid for by the government, so it is relatively free of charge to researchers. Now, those approaches allowed us to develop a variety of mechanisms of behavior of different biomasses. Well, I'm not going to go into details here, but essentially what we really wanted to do is to develop a mechanistic model in order to understand a variety of physical phenomena and also chemical reactions to get the type of products that we wanted to get. So starting with biomass, hydrolyzing it, and then catalyzing it, and then gasifying it. In our case, the purpose was to develop either a synthetic gas, which is a combination of hydrogen and CO, and later on, what we really, really wanted to do is to focus on generating hydrogen. And it's not just generating hydrogen per se, but rather generating hydrogen on demand. So it is just in time and just in case, in order to avoid costly storage. So that's the mechanism that we were able to do. And at the same time, of course, if you deal with biomass, then you're going to have some solid residue. And we were able to develop the process for biochar that allowed us to delignify the original biomass, the initial biomass samples, the way that we were able to reshape the solids the way that they were able to be used in a variety of practical applications, such as we were doing it in the house buildings, for example. However, perhaps the most intriguing and interesting approach that we were able to develop is to work with on hydrothermal flames. Now, why it is important? That's the work that we've done actually with NASA. That's what Canadian Space Agency and NASA are interested in applying hydrothermal flames in order to deal with a variety of applications in space at zero gravity. So we were using different organics, mixing with oxidants, and then initiating ignition and then using hydrothermal flames. So, for example, one of the applications that we foresee is to utilize hydrothermal flames to propel rovers, vehicles that at one point hopefully will land on Mars, go around and hopefully bring some samples back. There are some other applications of important applications of supercritical flames, supercritical water flames or hydrothermal flames, which is to use them to destroy both chemical toxins, and also biomedical waste. I have to say that we were testing it out how those flames would be able to deal with a variety of biological agents, including viruses, and it was a very interesting work. It's still ongoing, so I wouldn't want to report on something that we are still testing out. But nevertheless, that is one of the applications that is very likely going to help dominate the market in the near future. In the little bit more distant future, there's another work that we're conducting on the next generation of nuclear reactors, generation 4 nuclear reactors, and we tentatively obtained some interesting results, although still preliminary, with regards to increasing significantly the efficiency of that generation of nuclear reactors. So I know that, for example, countries like China or Canada, we are investing quite a lot in nuclear energy, so it would be quite likely important to understand these applications. Now, the experiments that we are conducting they are being conducted in the reactor that was developed, designed, and manufactured at NASA, and then that was shipped to us here in Canada. It's a beautiful engineering. Essentially, the key element of it is here. This is the reaction chamber that allows to both monitor and also collect samples from the reaction area where we develop a flame, and that we are able to measure temperature both along the flame axis but also across the flame radius. So that is the essence of the SCW, NASA's SCW flame machine. We are now working on the next generation of it. Whenever you work with flames, and especially with very exotic and unorthodox flames, which are flames in water, especially in supercritical water, the key element to understand is ignition. How to go from no ignition region to ignition region, that is going to be critical, especially at the time when potentially we would like to use this kind of propulsion for Mars rovers some years in the future. And there are a variety of parameters that define the behavior of flames and also influence the ignition. In general, what we would like to do is to ignite those unorthodox flames at as low a temperature as we can and as quickly as possible. So we analyze a variety of those parameters, and I'll show just a few that perhaps are important. So what one of the key parameters was to the temperature of the oxidizing agent. In our case, we were using a variety of those oxidants, so it could be hydrogen peroxide, and it could be oxygen, and it could be air, and depending on the temperature, the higher the temperature of the oxidant, the lower the ignition period, and it is a significant difference. I mean, almost 3 times lower. That translates to tremendous savings from the economic perspective. So that the regular distribution at temperature of 250, you can see that there was not very much happening for quite a long period of time until there was an ignition. With regards to 450 degrees C, we were able to see a bit of fluctuation, but then a significant increase in temperature. By the way, those TD, they refer to those points that I'm showing. Just B is just above the nozzle at the beginning of the flame, and D is at the midpoint of the flame. Now, so those are the important comparisons, and for the type of hydrothermal flames, some simple fundamental observations are not very easy to get done, especially if we want to make sure that we are understanding the properly parametric studies, because of course how it works, you have to fix all of the other parameters and then see how the temperature influences the type of parameter you are interested in, and then you have to multiply those experiments and involve other parameters. Then what I wanted to do is very quickly share with you the tests that we were conducting together with NASA at 0 gravity. So, of course,
Janusz,
yes?
you have 5 minutes.
Yes, yeah. Oh, that's perhaps the last slide. Yes, so at 0 gravity is very interesting, because at 0 gravity propagation of flame is very different. So I'll just show you here. This is at the normal gravity, which is a regular behavior of any flame. So it is propagating predominantly upwards. At 0 gravity, the propagation there is a significant propagation towards a radius. That means that after a predetermined period of time, the flame can fulfill the entire volume of the chamber. Now, so I wanted to, very quickly wanted to offer some observation overall about the roadmap, how I see perhaps approaching similar phenomena from the perspective of bolstering academics and how to foster engagement, including international engagement. So, well, as always, we have to establish a certain reference point, and we have to take into account what's happening in higher education, what are the perspectives all over the world, and how the Industrial Revolution is affecting what we do and how we do things, and why we do those things. Now, then from the academic perspective, we are looking at the challenges and the key elements defining our community, such as faculty and students and partners, and then translate it to a vision that is based on creating those partnerships, on creating research culture, and how people are going to interact. And I believe that there is a very strong possibility and necessity for us in science and engineering to collaborate with colleagues from humanities and social sciences and to engage with industrial partners, local community partners, and partners from all over the world. And only then, I think, we will be able to find meaningful solutions, and how we will be able to look at financing those solutions, looking at the strategy and thinking big, but starting small is always a good approach. This is all, of course, integrated, and that is the potential roadmap for some of the partnerships that hopefully this seminar, this symposium, is going to develop. So I wanted to stop at this point and thank you all very much for giving me this opportunity, for sharing some of the ideas that we have developed recently. Thank you again. I just stop here.
Janus, thanks for your wonderful lecture. Now the questions.
Nice to meet you, Mr. Professor Kozlowski. Thank you very much for sharing your deep thoughts about the life education and communication since at the beginning of the presentation. Thank you very much. And I'm Li Sha. I'm from Nanjing University of Technology. I'm also doing research about supercritical water gasification. Recently, I'm working on some work for synthesis metal oxides in supercritical water. So I have two little questions about your research on SCWO. The first one is I want to know that the SCWO equipment you built with NASA is batch reactor or continuous reactor. And the second question is when you do the experiments, did you observe some pressure variation if hair organic or hair concentration of the oxidation was fed into the reactor?
Yes, but thank you for asking. Great questions. So your first question was about the reactor. So indeed, this is a very flexible reactor. You can operate it as batch, you can operate it as continuous reactor. But we've developed and built a variety of other reactors, especially for SCW, for SCWO and also the supercritical water gasification. Be happy to share some details with you. Perhaps the easiest way would be if you come and visit us here in Canada. I'll be delighted to invite you so you can take a look yourself, and even if you wish, you can conduct some experiments. With regards to variations, indeed, we've pressure variations. Indeed, we've seen quite a substantial variations, but we were able to reduce it by adjusting appropriately the differences in flow between the reagent and the oxidant. So it looks like that it is in an inherent property of the system that you will always see those variations, but also it's a very important element to understand that what causes them and how you would be able to mitigate it. Because what you want to do is to avoid as much as reasonable those variations, because you would like to have very good repeatability of your experiments. Great question.
Okay, thank you. Thank you.
We have another question. We have maybe just one question.
Okay.
Okay, any question? And I have a question, Janus. And
then there is a question from XGX.
SGS. Now, my question is for yourself, diamond areas, you use the SR synchrotron light in Saskatchewan, and what samples did you analyze?
Yeah, so we analyzed biomass sample. So we had the diamond anvil cell. We placed it in the one of the synchrotron beam lines, and we used samples of biomass from British Columbia. Those were the residues from forestry industry. Those were the forests that were destroyed by a variety of insects. So what is happening typically, those are decaying and releasing plenty of methane. So what we did is we found a way how we would be able to reprocess that kind of forestry residue biomass. And there are some applications that are being now implemented in the forestry industry in Canada. Essentially, they are producing energy and ultimately electricity from those decaying wastes.
Okay, thank you. And now, Janusz, you are the host for the morning section. Please.
Okay, thank you so very much. I'm absolutely delighted to introduce the first speaker. You've already met Professor Tao Zhang as the Vice President of the Chinese Academy of Sciences. I should perhaps mention that Professor Tao Zhang, he received his PhD from the Institute of Chemical Physics in Italian, and then he spent some time in the UK, in Birmingham, and the university I visited as well, so I can rely somewhat to what he had done. Now, I think if you look at Professor Tao Zhang's biography, it is absolutely extraordinary. So if you allow me to share only a few elements and then direct you all to his extensive biography, he is a member. He is a member of the editorial boards of a variety of publications, influential and important publications, the journals like Applied Catalysis B or Green Chemistry. He's got more than 600 publications and astonishing number of patents, more than 100 patents. That is truly extraordinary. I'm also delighted to say that he became a fellow of the Canadian Academy of Engineering about 2 years ago, and his subject today is he's going to talk about conversion of biomass to ethylene glycol, and he is going to look at it from both the fundamental research perspective and industrial applications. So, Professor Tao Zhang, the floor is yours.
Thank you. Can you hear me? Can you hear me?
Yes, we can.
Okay. Thank you so much, Professor Kozinski. And also, I would like to thank Professor Zheng Fang for his very kind invitation to me. It's my great honor, privilege to deliver a talk in this very interesting symposium. The title of my presentation this morning is Biomass Conversion to Ethylene Glycol from Fundamental Research to Industrial Application. I think everyone in this symposium now, the biomass is the only carbon-containing renewable source and it's a very good feedstock for the synthesis of renewable chemicals and fuels. Different from other renewable energy, biomass, they will provide atoms of carbon, hydrogen, particularly oxygen. This is quite different compared with the oil. So this is demonstrating a very unique advantage. China, probably you know, declare they will reach the carbon peak by 2030 and achieve carbon neutrality by 2060. This is a very big country, and also we are a developing country, so this is a very tough tactics for our country. But this carbon neutrality policy will further stimulate the biomass conversion, exploration research, not only in China, but also around the world. And also United States and Canada, they declare carbon neutrality by 2050. This is a China strategy about carbon neutrality. You know, China is a very big country, so we need a different kind of energy. Any one kind of energy is not enough for China. So now the oil, you know, we input more than 70% oil, and the natural gas about 50 natural gas. And the coal, we are very rich in coal. So the coal is we can use it for several hundred years. So this is our main energy source. But now, you know, in China, we developing wind, solar energy. This is ranking #1 in the world. And also we pay much attention to biomass. So this is renewable energy in China. And also we pay much attention to nuclear energy. We are very happy to know United States declared yesterday a very big breakthrough for the nuclear energy. And also we have a very big team working on the nuclear energy in China. So this is a comprehensive system in China. We need to combine all the fossil energy, renewable energy, and nuclear energy together to build a comprehensive comprehensive energy system in China. Particularly, we need to combine the renewable energy together with the fossil energy by some platform molecules, for example, the carbon dioxide, hydrogen. So this is currently our strategy in China. For the biomass, this is important focus on the biomass. So I would like to focus on the biomass. You know, there's the biomass, cellulose, lignin, hemicellulose. So biomass is the main composer of cellulose, hemicellulose, lignin. Particularly the oxygen is apart from the carbon and hydrogen. This is a very unique properties for the biomass. So why biomass glycol? Because the title of my presentation is ethylene glycol. Because glycol, this is oxygen containing. So we can use all the atoms, not only carbon, hydrogen, but also the oxygen. So this is the ethylene glycol and 1,2-propylene glycol. So ethylene glycol and 1,2-propylene glycol are crucial bulk chemicals. Currently, it's from the petroleum source. The consumption of glycols is more than 30 million tons per year. And also they increased about 5% every year during the last decades. The catalytic conversion of biomass to ethylene glycol is highly attractive due to its renewable feedstock, high atom economy, and green process. So we pay much attention to the biomass to produce ethylene glycol during the last decades. Challenger. in the biomass conversion to ethylene glycol. This is hemicellulose, lignin. Particularly, we pay much attention to the cellulose. This is about 1/3, more than 1/3 in the lignin cellulose. So the challenge is to break the bit 1,4 glycoside bond to produce polysaccharide, and then to break the carbon-carbon bond, then produce such kind of hydrocarbons. Then further to break carbon-carbon bond and do the hydrogenation reaction, we can produce ethylene glycol. So this is a very promising reaction, but we have many challenges how to selectively convert the beta 1,4 glycoside bond, and how to selectively convert the carbon-carbon bond. I have mentioned ethylene glycol currently, is from petroleum route. They produce from the ethylene currently, the majority way. And also in China, because the coal is very rich, so we can produce the ethylene glycol by the carbon 1 chemistry. That's to from the coal to produce syngas, and then from the syngas to produce ethylene glycol. But now the biomass is challenging, but it's a very promising process because we can use not only carbon, hydrogen, but also we can use the oxygen in the biomass. So this is a very atomic economy. So we pay much attention to this process. We are very lucky. One of my students, Miss Gina, now he's a professor in Tianjin University in China. 14 years ago, we published a paper in Agrochemie. Now it's more than 15 years. We are very lucky to find a very unique catalyst, nickel-promoted tungsten carbon, supported on the active carbon. So we can, from the cellulose, by one pot to produce ethylene glycol. This is a very new reaction. We are very happy to discover such kind of new reaction to produce ethylene glycol from cellulose by one pot process. And also we filed several patents during the last decades for such kind of new process. And after the first paper, we need to understand the reaction mechanism. Why we can use such kind of catalyst to selectively convert cellulose to finally to ethylene glycol. Now we can understand the first step, use the acid catalyst, do hydrolysis from the cellulose to produce the polysaccharide or glucose. Then we can have a rich-order condensation reaction by the tungsten catalyst, then produce the glycolaldehyde. This is glycolaldehyde is a very important intermediate compound for our process. Then from the glycolaldehyde, by the ruthenium or the nickel, any hydrogenation reaction, we can produce the ethylene glycol. So this is a very interesting new reaction from the cellulose to produce ethylene glycol. We understand the reaction mechanism in a more detailed way. So this is cellulose by the acid catalyst. We call the reaction 1. We can produce the glucose or oligosaccharide. And now if you do the reaction, this is a rich-order reaction 3. So we can produce the ethylene glycol. But if we do the isomerization reaction, This is reaction 4. Here you can find is the isomerization. So you can produce fructose. Then do the hydrogen, do the ritual auto condensation from the fructose. They can produce different kind of compounds. Then you will produce 1,2 propylene glycol or glycerol, and all even from the reaction 2, this is the hydrogenation reaction, fructose to hydrogenation reaction, you can produce the mannitol or sorbitol. So this is a very complicated reaction, but if you use a very unique catalyst, you can control the reaction to this way, to ethylene glycol. Of course, you can modify your catalyst to produce more 1,2 propylene glycol, even the mannitol or sorbitol. So this is a very interesting process. We have understand the reaction mechanism during the last 10 years, last decades. And also the kinetics. We do a very detailed kinetics study. So you can find this is the reaction rates comparison, different kind of reaction, cellulose hydrolysis, ritual auto, hydrogenation reaction, glucose hydrogenation reaction, and glycoaldehyde degradation. So you can find our results show the glycoaldehyde hydrogenation reaction rate is very fast compared with the ritual auto, and very fast compared with hydrolysis reaction. So this is a rate determining reaction for the hydrolysis reaction. During the last decades, we published more than 60 papers to study detail for such kind of reaction, and we feel 70 patents. We try to commercial such kind of process, so we feel a lot of patents during the last decades. So. Because of time limit, I would like to mention several milestones for our new process. So we started the research of biomass conversion from 2006. Then after 2 years, we discovered such kind of new reaction for cellulose to produce ethylene glycol. And we have a very detailed study for the reaction mechanism, and we design and obtained a low-cost catalyst. This is a very key, very important for the commercialization reaction. And also we need to try our whole biomass conversion, because the fundamental research is to use the pure cellulose. But now for the commercialization process, we need to use the whole biomass. And also we need to design a highly efficient process. Now, for the industrial demonstration during the last 4 years, from 1918 to this year, we use about 3 to 4 years to make an industrial demonstration in China. So we are almost close to the success for such kind of new process. Use the whole lignin cellulose, and then one pot chemical reaction to produce ethylene glycol. Then ethylene glycol do the polymerization to bio-PET. This is our products, bio-PET from the bio-EG in our laboratory. We design such trademark for the process, DLEG. This the meaning is direct lignin cellulose to ethylene glycol. And also we have another meaning for our new process, because we are our city in Dalian, in China, in Dalian. So Dalian ethylene glycol. This is our logo, DLEG. I hope you can remember such kind of new process in the near future after our commercialization. So in 2019, we kick off a ceremony in Puyang in Henan, China, for our 1,000 ton per year pilot demonstration. After 2 years, we construct successful the facility, the pilot plant in Puyang, Henan. This is a huge work for the design, such kind of 1,000 plants, pilot plants. You can find the design documents. It's a huge amount. And also the construction size, a lot of work. The container reactors, and finally, the end of last year, and almost we finished the construction. Our pilot demonstration is 1,000 ton per year cellulose to bio-EG in Henan, Puyang, China. This is probably the first pilot demonstration from cellulose to bio-ethylene glycol in the world. And this is our products, bio-ethylene glycol. You can find the purity, the selectivity is very good. We can obtain about 85% the selectivity. The purity is more than 99%. So I would like to try to summarize our DLEG pilot demonstration. The design of the reactor at a metric scale is verified. This is, we use such kind of reactor, we can obtain a very good mass and heat transfer. And also the catalyst performance has been verified. The selectivity is to ethylene glycol is higher than 85%, even better than the result in our laboratory. So the result from pellets 1,000 ton per year, the selectivity is better than in our laboratory result. In the laboratory, it's about 70%. And also the product distillation system is tested. We can now we can have a purity more than 99%. In the near future, we will improve our distillation process. We can obtain even more purity, higher purity for the ethylene glycol. And also the purified biomethylene glycol has an optical purity very close to the standard of ethylene glycol for PET synthesis. The operation parameter, we have collect all the parameter. This is a very good foundation for the design of reaction process package for the DLEG at a scale of 100,000 ton per year. We hope in the near future we can design such kind of package, reaction process package for our commercialization of such new process from cellulose to ethylene glycol. And also the perspective and the conclusion. You can find our system study and endeavors have been made on our new process for the biomass conversion to ethylene glycol in the past decades. This progress, including the robust and low-cost catalyst, reaction kinetics, high efficient reaction system, feedstock influence on the reaction, and bio-EG purification and application for PET synthesis. They paving a solid way for DLEG process application in a large scale in the near future. The pilots at a scale of 1,000 ton per year has been built and operated successfully, making a good foundation for DLEG industrial application in the near future. To promote the DLEG left. Okay, almost finished. I would like to mention some opportunity and challenge for whole biomass conversion. So the industry currently, based on the biomass and the fossil energy, you can find petroleum, natural gas, and coal. You can produce a gasoline, kerosene, diesel, benzene, toluene, xylene, and For the biomass, of course, you can do the pyrolysis to produce the crude oil and then upgrading to produce gasoline. And also you can do the catalysis pyrolysis to produce the benzene, and also you can produce the ethylene and propylene. But for the oxygen-containing chemicals, you can now, For the oxygen-containing chemicals, now from the petroleum, you need to do the oxidation reaction, put the oxygen. For the biomass, this is very good because you don't need to do the oxidation. So this is very unique from the biomass to produce the oxygen-containing chemicals. The advantage, so the oxygen is very important for the biomass conversion. And we have various functional group, abundant, cheap, and renewable. 5 and 6 members ring structure facilitate the synthesis of new material for the future. This is particularly zero carbon emission. So this is very important for the biomass conversion compared with the fossil energy. But we have a very big challenge because the very complex structure and also very limited thermodynamic data, and also the recycle, the catalyst. We need a low-cost catalyst, and also we have a lot of challenge in the future. We need to do a lot of work, and for the biomass resource, we need to design the new technology to make such kind of biomass conversion available in the near future for the commercialization. I would like to thank my colleagues, Professor Aiqing Wang and Professor Ming, and they helped me do a lot of work. And also I need to thank my international cooperators, Professor Harper in the United States, Professor Mo in Taiwan, and Professor Wilson, Adam Lee in UK, and Professor Bert in Belgium. And also, of course, I needed to thank our government and also our partners company to provide financial support for our fundamental research and also for the pilots demonstration. This is Dalian Institute of Chemical Physics, located in Dalian, a beautiful campus. I would like to invite all friends to visit Dalian in the near future. Thank you.
Thank you so very much for the presentation. It's truly comprehensive one, and congratulations on doing something that is not easy to get done, which is taking doing it in a transformative way from a scientific breakthrough to industrial applications, plus developing a very elegant logo. So very well done indeed. Let's open up. Pleasure. Let's open up your presentation for questions. Do we have some questions?
Hello, Professor Zhang.
Please go ahead.
Please.
Yeah, Professor Zhang, it's a wonderful speech. And my name is Shuai from Professor Fang's group, Nanjing Agriculture University. So I have 2 questions. The first question is to convert the cellulose to the chemicals such as the BioEG. So is it very important to separate the lignin from the cellulose so that can we have a high efficient transfer to the chemical? The second question is about the pellet plant. So I'm very glad to see the setup of the pellet plant. So just wondering, what's the yield of the BioEG from the DLEG process? So is there any byproduct? So, and also any idea about the utilization of the byproduct? Thank you so much.
Okay. Thank you. Very good questions. For the purification is one of most important challenger, even for our group in the future. I have shown you the purity now is more than about 99.5% currently. So we need to improve our purification process to obtain a higher purity in the near future. So this is one of our challenges in the next year. And also about the yield. I have mentioned the selectivity is about 85%. It's even better compared with the result we obtained in our laboratory. So now the yield is, the conversion is about 100%. So the yield is about 90% based on the cellulose for our commercialization process in the future. About the byproducts is we have a 1,2 propylene glycol, and also we have some little amount about carbon-3 and even carbon-5, carbon-6 oxygen-containing compounds. It's very complicated. Thank you.
Thank you very much. It's very clear. Thank you.
Thank you. Great answer. Some more. We have time for more questions. So, anyone?
I'll try one.
Richard, yes, please.
Yes. Thank you so much. It was very educational and a beautiful presentation going from laboratory to almost final product and logo. And I'm wondering on the pilot plant, what is the source of biomass going to be?
Good.
And then what type of pretreatment do you imagine for this type of, to remove all of these purity issues?
Yes. We have some cooperation with Shandong province, one company in Shandong province. The source is from coal stock, the corn.
Corn.
Then corn from the corn. This is very important for the pretreatment. It's also one of very challenging process for our reaction. It's a very good question.
Thank you so much.
Thank you.
Thank you, Richard. Other questions? Yes, please.
Yes, please.
Sarani.
I'm Sarani from Malaysia. I just want to ask you about your polyethylene. Are they biodegradable or similar to the current polyethylene from petroleum base?
Sorry, would you repeat again?
The biodegradability of your polyethylene, are they similar to the current polyethylene from petroleum base?
No. We have not did such kind of degradation, so I believe they will have a very similar property because after purification, so the ethylene glycol purity is almost close to the petroleum-based ethylene glycol. Probably it's almost same, but we need to do we need to do work in the future. Thank you for your very good suggestion.
Because of people now concerned about the environment, with the single-use plastics and so on and so forth. So they are looking to the biodegradability of the materials compared to the current petroleum base. That's why I'm asking.
Yes. Yes, a very important question. I will do such kind of work in the near future to compare with the degradation of bio-based PET and petroleum-based PET. Very good question. Thank you. Thank you for your comments.
Thank you. Perhaps one more question, because there will be some photos taken soon. I'll make if there are no questions, just curiosity. Actually, it's mostly about. Excuse me, there is a question.
Yeah. Here it's Yan from Yan.
Please go ahead.
Yeah. Okay, thanks, Professor Zhang, for your super impressive presentation. I just have a very simple question, is that the result of your experiment shows the catalyst is very efficient for promote the cells to transfer to EG, but is it also work for heme cellulose or lignin? Use the same catalyst?
Yes, for such kind of catalyst, we have a published paper in EES. If you have interest, you can read that paper about 10 years ago. With such kind of catalyst, lignin also can have some conversion to produce aromatic compounds in our system. So now we try to separate the lignin first, then do the cellulose conversion in our process. Thank you.
Okay, great. Thanks, Professor Zhang.
Thank you.
Thank you very much. So just one curiosity question, mostly about economics of the process. How would you compare the cost of create or developing ethylene glycol from biomass versus if you have the product and then the financial benefits of application of that?
Yes, very good question. This is one of the challenger for our society. So I have one slide. I have one slide to show you the comparison between the down, please. Could you no. This, okay. Yeah, this is a figure probably give you one answer here. If our society ask carbon tax here, this is a biomass green here. Now it's higher, the price is higher than the oil-based and coal-based. You know, in China, coal-based is even cheaper currently. Yeah. But if the carbon tax, we have a carbon tax, the government if have a carbon tax. So finally, here, it's about here. Now, if you do carbon tax here, they were cheaper compared with the coal EG. So about 200 Chinese yuan is about 50 US dollar. 50 US dollar. We do some evaluation.
Yes, I can see. Thank you so much.
Thank you.
It's a terrific clear answer.
Thank you.
If there are no further questions, I can see that Professor Fang is ready for a great photo. Then, so how would you like to proceed? Because I believe photo will be taken for those participants who are there on site. Is that right?
Maybe everyone just open our camera, then we took a photo together.
Ah, perfect. Let's then do it.
Okay, then the first picture. Second picture. Okay, that's all. Thank you.
Once again, good morning, colleagues. It's exactly 10:40, so perhaps it's time for us to move to the next presentation. I can see that our speaker, Professor Boxing Han, is already available. So if I may, I will introduce the speaker, and then we very much look forward to your presentation. Professor Boxing Han is the academician at the Chinese Academy of Sciences. He's a fellow of the World Academy of Sciences and a fellow of the Royal Society of Chemistry in the UK, I believe. And he's got plenty of different accolades, including being a chief scientist of China Innovation Think Tank and being a chairman of Green Chemistry Division, sitting on a variety of editorial boards, including editor-in-chief of the Innovation. His research includes studies of physical-chemical properties of green solvent systems and their applications in green chemistry. And that's, I believe, that's what we will be hearing from him today. His title of his presentation is Conversion of Biomass into Chemicals and Fuels. It's your floor, Professor Han.
Everything is okay, right?
Yes, everything is fine. Please go ahead.
Good morning, ladies and gentlemen. And first, I thank the chairman for wonderful introduction. I also thank the organizing committee for giving me this opportunity for give this talk. So today, I will talk something about the conversion of biomass and into chemical and fuels. First, because I'm working on green chemistry, I would like to introduce green chemistry very briefly. We know that chemistry, is and the chemical industry is very important for our human being because chemistry and the chemical industry create numerous new chemicals and materials. And we know that without chemical industry, without chemistry, we can't have a happy life. Everybody knows this. I will not discuss this in detail. And however, we know that conventional chemical industry produce huge amount of waste. So how to realize sustainable development of chemical industry is a very important task for us. The green chemistry is a way for sustainable development. Yeah. I would like to also talk about something about green carbon science. We know that carbon is also very important for human being because in our body, we have about 18% carbon. Without the carbon, we have no human being, no ourselves. Also, we see we are varying carbon, we are eating carbon, we are living in the carbon, we are using carbon anywhere. And then also we know this, and from the carbon resource point of view, and the carbon resource is also indispensable for us. We have non-renewable carbon, we have non-renewable carbon resource such as coal, petroleum, and natural gas. And we also have renewable carbon resource such as biomass and CO2. Yeah. However, when we are using carbon, we cause many problems. We make pollution, and also you see the non-renewable fossil resource. They are non-renewable. They will finish in the future. And so, how to use the carbon resource efficiently and cleanly is also very important task for us. And we are meeting challenge here. And in this situation, Professor Mingyuan He, he proposed the idea of green carbon science, and we wrote 3 papers about green carbon science. We gave a definition, what the problem when we are using carbon resource, and how to solve this problem, and how this green carbon science relates with carbon neutrality. So we propose so some idea on this, and here you see we know that efficient utilization of fossil resource and the economic process to use biomass and CO2 is very important issues. Now I would like to talk something about our some work in our group. So actually, I'm working in the interdisciplinary area of green chemistry and physical chemistry. So we are working on green solvents such as supercritical fluids and liquid water and the switchable solvent, and we studied their physical properties, and also we design some green solvents, and also we design some catalytic materials using the special feature of green solvent, and we also carry out different chemical reactions in green solvents. So you see, for example, we carry out a number of work reactions for conversion of CO2, biomass, and the waste plastics in green solvents. Now, you see, we know that this using of this renewable and recyclable carbon resource is crucial for sustainable development, and they can be used to convert into chemicals, fuels, and materials. And now I would like to talk, because today is about the biomass, so I would like to give some examples about our recent work for conversion of biomass into chemicals and fuels. And this is very important because you see, for human being, we have two important issues. One is sustainable development, another is carbon neutrality. Actually, we know that utilization of biomass relates with both of these very important issues. And also is here, we design a number of catalyst green solvent systems, and we develop some new routes for biomass conversion. We can convert biomass into surfactants and ketones, alcohols, acids, organic acid, benzene, phenol, and nitrogen containing chemicals. And I give some example here. We know that lignin is a very important biomass, and it is abundant, and it also the byproducts in some chemical industries such as paper industry. Each year we produce about 50 million tons of lignin. How to use this lignin? Of course, it's very interesting, and we know that by the polymerization of lignin, we can get, you see, the ethers, you see, get this structure, and how to convert this kind of structure into more valuable chemicals. That is, we can broaden the utilization of lignin, you see. So we carry out some work on this. The first, for example, here we design some catalysts in water solvent, and we can efficiently convert ethers into ketones here, and the yield can be as high as 96%. And here, another example is, you see here, for the ethers, you see here, and we can get benzene and the derivatives. People have done a lot of work on this, but other people use hydrogen as a hydrogen source. We consider the structure of this kind of material, and we know that, you see here, the methyl here, that CH3, they have hydrogen atom here. We can use this hydrogen without any hydrogen gas that is desirable. So we design some catalyst and green solvent system. You see here, we use hydrogen here. We can get the benzene and the derivatives, you see here. And it's very fortunate that we can get 100% yield, you see, for different substrates. You see here, with different group here, we can get benzene and the derivatives here, and the yield is very, very high. And we can also use this method for real lignin. You see, we can get 8%, more than 8% benzene here. And also another example is that, you see here, we know that anisole, we can get this from natural products. We can also obtain this chemical from depolymerization of lignin is here. If it can react with carbon monoxide, that's CO, that we can get if we can get some esters. That is a very important reaction, but it's very difficult to realize this reaction. We design catalyst and ion liquid catalytic system because the synergetic effect of catalyst and ion liquid, we can carry out this reaction very smoothly, and the yield can reach about 98%. Nearly all of this can be converted into esters. You see, for different substrates with this group, we can realize the reaction here. And also, you see here, we know that you see for cleavage of carbon bond, in many cases it's a key for conversion of biomass for lignin in the biomass into useful chemicals. So we found that you see nitrogen dioxide, you see here, NO2. You see here, we can use this gas as a catalyst, and we can cleave the carbon bond here very efficiently. And you see here a number of substrates, we can convert them into organic acid. You see here, you see different. We try a number of reactant here, and the efficiency is very high. And we also know that the phenol is a very important chemical product. You see here, and you see if we can produce phenol from lignin, that is very desirable. And we develop some molecular sieve, some catalyst in water, combined with water, we can carry out this reaction. You see here, the selectivity can be higher than 90%, and the yield of phenol can be about 11%. Actually, this we convert most of the group into phenol here, and this is a very green and efficient route. And some years ago, actually, we carried out reaction for conversion of phenol into this cyclohexanol. You see here, this one is a very important chemical for producing polymers, and can be used as solvent for many things. You see here, and but selectivity usually is very low because this chemical can be further hydrogenated to this. That is not desirable. So we design some palladium Lewis acid catalytic system. We found that in supercritical CO2, the selectivity can be 100%. That means at complex conversion, that means the yield can reach 100% here. Now we can say from lignin, we can produce phenol, and from phenol, we can produce this very important chemical. Now we can say this chemical can be produced from lignin. Also, benzene is another very important chemical you see here. And if we can produce benzene from lignin, it's also very interesting reaction you see here. And but cleavage of carbon and the carbon oxygen chemical bonds is the key for carry out this reaction. So we use water as solvent. We design some catalyst. We can realize this reaction. You see here at the optimized condition, we can we can get 20 grams of benzene from 100 grams of lignin. That means 20%. That is approach theoretical value. And based on control experiments and theoretical calculation, we propose the reaction pathway you see here, but I will not discuss this in detail today. And also, we know that critical, you see here, this one we know that is a platform chemical for utilization of lignin. You see here, because you see here OH group and this ether group, and we can get different chemicals. But we know that you see here, but how to selectively get one chemical is very important. and Professor Zhang in Dalian University, they propose they carry out first work for a single atom catalyst that is very unique for many reactions. So we use single atom ruthenium as a catalyst. You see here, you see, because the unique feature of this kind of catalyst, you see the yield can be approached 100%. That means no byproduct can be produced. Then we study why the single atom catalysts are very efficient based on theoretical calculation and experiments. We gave the reaction pathway. Anyway, we think for single atom catalysts really have their unique features for many reactions. I think that is very promising. And we also know that when people we are producing chemicals from lignin, we always think about we can cleave them, we can depolymerize them into chemicals, but usually we get mixtures, you see here, and how to get pure chemical from lignin conversion, that's also very interesting. And we know that, but we propose the idea is that, you see, if we selectively convert, utilize one group, one part of lignin, we can get pure chemical. So we know that in lignin there are more than 10%, you see, this kind of group, you see, methyl group, you see here, CH3 group. There are many groups like this. If we can selectively convert this, and then we can get pure chemical. So we design green solvent and the catalyst system used here. By reaction of CO2 and water, we can get pure acetic acid. In 1 gram of lignin, we can get about 20 grams of the acetic acid here. And also we can use CO2 and hydrogen carry out this reaction. We can get ethanol and acetic acid. So that means if we can selectively convert some group in lignin, we can get pure chemical. You see here, the left lignin, they are OH group. Then they are more for the hydrophilic. That's more useful. That means we can use the lignin very efficiently here. And we also do some work on conversion of cellulose. I give some example on this, and we know that, you see here, and we know this chemical that called levulinic acid and its ethers, and they are platform chemical for utilization of cellulose. And if we can use this, if we can produce some nitrogen-containing compound, that is also very, very desirable. And because these kind of chemicals are very useful for many aspects is here. But how to convert this efficiently is the key. So we design some catalysts, for example, with palladium, and here we can design support on this support, you see here, and we can carry out this reaction very efficiently, and for many reactant different here we can get this chemical, and we try more than 30 kind of substrate here. We can get this kind of chemical very efficiently here. And also, just I mentioned that single atom catalyst is very useful and very powerful for many reactions. Here, I would like to give another example here. Is here, we know that this HMF is a platform chemical for conversion of cellulose is here. If this chemical is here is called fulfil, you see here is also useful. And how to carry out this reaction, convert of HMF to this. People have done a lot of work on this, but the problem is that, you see here, on this chemical, we have 2 groups. They can be hydrogenated together at the same time. How to selectively convert this OH group, that is challenging. And the people also realize this group, other people, they use, you see, they convert with react with some other chemicals to get it kind of one chemical intermediate, and then they hydrogenate this one to this one. They have two steps. So we use single atom palladium catalyst. You see, supported on some support. You see here, we found that this is without this in the step, without just one step, you see, we can convert this one into this with a yield of larger than 99%. That means, but we studied the reaction pathway, reaction mechanism, but because time is limited, I cannot discuss this in detail. And but anyway, I say for single atom catalyst, it's very useful and very promising kind of catalyst. Yeah. And here is another example. And also we prepare some materials using biomass. For example, we prepare some surfactant using biomass, and just use a combination of liquid and the biomass. We can get some surfactant, and we can emulsify some chemical reaction. Using this, we can get the emulsions, and we can emulsify some reaction system. We can get a higher reaction rate, higher reaction efficiency here, and
5 minutes left.
We can use biomass, you see, as a produce some catalyst. For example, here, phytic acid here, you see, we know that it has 6 coordination groups, polar groups. They can coordinate with different metals. Using these natural products derived chemical, and we can produce some porous catalysts here. You see here we get some complex with different metals here, and we found that they are porous and with a very wide size distribution. And this one, we found that because of multi-porous material, they are different size of pore, and they are very efficient for this reaction. That is platform chemical of cellulose, and also we can have this. People know this reaction, but our new catalyst is very efficient. You see here, for example, using our catalyst is 99%. You see here about 96% yield, and but if we use same metal using MOF, that means the metal framework, the conversion selectivity is much lower. And the selectivity of our catalyst is also very stable here. And also you see for this reaction, I give another example is that you see here, well, we usually use metal catalyst by homogeneous, we can support them on some support. But we found that if we can prepare porous metal without any support, they have a large pore and very metal pore, this kind of structure, they are very efficient for these reactions here. You see, for our catalyst, you see here, we can reach 100% yield very quickly, but for commercial, for the same amount of metal, for conversion for commercial catalyst, you see the efficiency is much lower. That means porous, multi-porous metals, so for some reaction, they can be much more efficient than supported catalysts. You see here, I just want to show this. You see here, I also gave another example for electrochemical conversion. We have produced lignin from lignin here, and by electrochemical reaction here, we can promote this reaction, this phenol with react with water. We can get the two chemicals at the same time, two very important chemicals at the same time. You see, the hydrogen in water can be used to produce this one, and in the anode is here, the oxygen can be used for this reaction. That means all water and these chemicals are used in the reaction. If the yield can be 100%, that is very high. Also, we carry out some photocatalytic reaction. For example, here I give one example here. You see, for this, for hydrogenation of this kind of chemical, people have done this for many years. And also for oxidation of cellulose is also interesting. And by photocatalytic reaction using water as a hydrogen source and oxygen source, we can here for oxygen we can oxidize this chemical of cellulose into different useful chemicals, but hydrogen can be used for this. That means photocatalysis is also very promising for conversion of biomass because time limited. We know that I just mention that utilization of biomass, we have a long way to go. In the future, we have to should consider the special structure of the biomass to develop more efficient reaction route. But I will not discuss this in detail. And finally, I would like to National Natural Science Foundation of China, Ministry of Science and Technology of China, and the China Chemical Science for the long-time support of our group. And I also like to, taking this opportunity, I also like to thank my colleagues, my students, and my collaborators for their for hard work. And finally, I thank you very much for your kind attention. I thank the organizing committee again for giving me the opportunity for presenting this talk. Thank you. Thank you very much.
Thank you, Professor Han, for truly elegant presentation and such a rich sharing of knowledge with everyone. We really, really appreciate it. Let's open up the presentation for questions. Who would like to go first? Yes, please go ahead.
Many thanks for your excellent report and your such many new reactions in
the
biomass.
voice is very, very weak. I can't hear very clearly. Yeah.
Okay, can you hear me?
Now it's better. Yeah.
Yeah, okay. Professor Hans, many thanks for your excellent report and your so many new reactions in biomass utilization. I have one question. As we all know, lignin is the important part in biomass, and you also designed several new reactions in lignin conversion. And could you give us some some advice in the lignin industrial application in the future?
Yeah, thank you very much. I think that is a very interesting question. Actually, that is very challenging. How to use people? We know that people have done a lot of work on conversion of lignin, but for commercialization, that is not as good as cellulose and some others, right? We know and the same in cellulose and how to relate commercialization. That is very challenging, is a very important task in the future. But I think in fact, I think even although it's a difficulty, but I think that's very promising. We can produce some functional materials using lignin, that's the special structure, because that is the only aromatic renewable resource in nature, and we can convert them into functional materials. But I would like to mention that when we design some reaction, we should consider there's the structure, because you see they have some CO bond, CH bond, and there are some functional group. We should consider their own future. Then, for example, we can convert them into aromatic compound because there are a lot of benzene ring in the lignin, and maybe we can break cleavage some chemical bond. We can get very useful chemical very directly. That means, I mean, for conversion, we can different ways for convert them into material, different kind of materials, and we can convert them into different chemicals and taking their unique structure. I think we have a long way to go. Yeah.
Thank you. Thank you very much. One more question, perhaps? Yes. Yes, please.
Professor Zhang, Sarani again from UK and Malaysia. Just to ask you, when you deal with lignin, it is very unstable, especially at high temperature, form radicals and tend to polymerize. And how do you handle the experiment when you are dealing with the temperature, high temperature, and with different types of catalysts to make the separation? Do you get a reproducible result?
Yes, I think you are. This is also very good question. It's a very interesting question. Actually, just as you said, the lignin, because they can polymerize, they can during the conversion, they can be polymerized and can be converted into different chemicals. That is the problem. But in our catalytic system, because we have no that kind of problems. But for some reactions now, one of my postdocs, he has worked for 3 years for this because they just protect how to keep some stable, some group, some compound stable, and how to do that. We will submit a very interesting paper very soon. But for the root, I talk today, we have no that kind of problem because we cut the carbon bond and carbon oxygen bond, then that kind of problem is not dealt with. We do not meet. We did not meet this kind of problem in our route. But in many cases, the problem you mentioned is very important. We have to consider about that. Thank you.
Thank you very much. Professor Han, thank you so very much for your excellent presentation. Perhaps we'll switch to the next presentation, and we may ask you actually to the switch off sharing so we can give sharing opportunities to our next presenter. Good evening. We've got it. Good evening, Professor Ruan. I believe you will be speaking from Minnesota. It's around just a few minutes after 9 p.m. Welcome to the symposium. Professor Roger Ruan, he is the professor in the Department of Bioproducts and Biosystems Engineering at the University of Minnesota. This is where he is also leading the graduate studies in the department as the director of graduate studies. He's a member of a variety of societies, both in the US and outside the United States. You will hear about his research, which is very interesting because it combines a variety of experimental approaches, including pyrolysis, gasification of waste in order to produce chemicals and materials and fuels and energy, of course. One thing that I liked very much, well, you will see his resume, it's quite extensive, but one thing I wanted to point out too is that he has supervised and graduated a significant number of graduate students. I can see it's 75 and even larger number of postdoctoral fellows and research fellows. And I'm certain that he also was directing quite a few undergraduate research theses. And this is very, very important. As important as it is for all of us to do publications and get grants and so on, but educating such a tremendous number of young people is extraordinary, especially looking at the stage of the symposium today. So, Professor Ruan, I wanted to pass on baton to you, and it's all you, and we are looking for sharing your knowledge with all of us. Thank you.
Well, thank you. Thank you so much for the nice introduction, Professor Kosinski. And I want to take this opportunity also to thank Professor Jen Fan for the invitation. I'm very pleased to have this opportunity to discuss some of our work on the sustainable solid and liquid waste utilization for circular and sustainable economy development. So, but before my talk, I need to give a public disclosure as required by the University of Minnesota, since we license pyrolysis technology to Resynergy. I'm also the chief technical advisor and owns equity in the company, but this interest has been managed, reviewed by the university. So now we know in China, for example, the number of pigs has reached over 400 heads, and the total manure generation reached almost 2 million tons every day. And then application is still the main method of manure utilization today. So the huge amount of this swarm manure puts pressure on both farms and the environment. And the large amount of this nutrient runoff have resulted in, nutrient losses and significant water and air pollutions also. So this picture shows how land application increased the nitrogen loads in the water. And a lot of these, I'm not going to go into much detail because of timing, but just want to, stress on this again. So, and this is the Minnesota statewide nitrogen source to waters on average precipitation. About 70% comes from the cropland and over 15% is from the manure application. So there are also significant amount of municipal and municipal solid and liquid waste. So here is the Minnesota's municipal solid waste characterization, meaning includes organics, papers, plastics, and so on. And, I assume different provinces in China are probably very, very similar. And we currently rely on landfills and waste to energy productions in some facilities, which to, waste processing from these municipal solid waste composting to making refuse-derived fuels. But these, can certainly, have better applications. So. And there are also a lot of wastewater available. We have 8 municipal wastewater treatment plants in Minnesota, for example, treating about 100 billion gallons of wastewater a year. And this is the St. Paul wastewater treatment plants. This is where I'm from. It treats about 200 million gallons of wastewater every day. And they are about 1 million gallons of central wastewater, which is the wastewater centrifuge, from these sludge, and that contains very high level of nutrients. And this is actually the characteristic of the central wastewater. The nutrient profile is actually perfect for the algae production. Therefore, we have successfully developed the algae productions using the central wastewater. And we have demonstrated the systems in our research and outreach centers and also on wastewater treatment plants. And the other streams of the municipal wastewater, such as sewage sludge and scums, also contains a lot of energies that could be used for heat and power and fuel production. For example, scums, that's the material floating on the wastewater. It actually contains a lot of oils, and it's a very good feedstock for the biodiesel production. So we have developed a patented technology to efficiently use the scum from the for the biodiesel production, pretty much completely utilizing all of the heavily used oils with very high free fatty acid content. So all these wastes present us many problems, but many opportunities too. We can use them to produce sustainable, produce food and feed and so on, and all convert to energies, chemicals and materials. And a key component of this waste management strategy should be the treatment through utilization, because that has many advantages as compared to the treatment itself. So let's look at various novel treatments through utilization technologies. The first one is an integrated biological systems for animal wastewater utilization. So much of the manure wastewater, for example, have been utilized through these anaerobic digestions to produce methane for energy production. So here you can see that the top here is the manure wastewater before anaerobic digestion, and this bottom one is after the anaerobic digestions. And you can see the COD levels even after AD is still have more than 70% remaining in the wastewater. Okay, so and then if you look at the total ammonia actually increased because during the process actually a lot of remaining protein breakdown, producing these, and so therefore total nitrogen is also very high. So if you simply using the AD and then the remaining wastewater used for that application, you will still cause all those pollution issues. So, we have developed an integrated biological systems for the animal wastewater utilization. We first add carbon source like corn stovers to adjust the CN ratio, and then we use thermal hydrolysis, and then we remove the AD inhibitors like the ammonia, because too high of ammonia, it actually will inhibit the methanogen for the methane production. And after that, then we use, these pretreated wastewater for the AD to produce methane, and then using algae cultivation and hydroponic vegetable productions, and then use the biochar to filter and condition the wastewater. So this way we can actually remove most of the almost all of the nutrients from the wastewater and recycle or reuse the wastewater. So this is a conditioning pretreatment systems to adjust the CN ratio and hydrolyze the substrate and remove the AD inhibitors such as ammonia and hydrogen sulfide using the vacuum. And this is the conditioned and pretreated wastewater can then go through AD. And you can see here, if we don't go through that kind of pretreatment process, the AD the production is very low. But with the these pretreatment, then methane generation, methane yield increase dramatically. And the post AD effluent, it may still contain too much of solids and other hazardous component, which can inhibit the algae growth. So we use a biochar filtration to remove these, and then the biochar could also help clarify the water for the algae cultivation. So this is, post, again, this post AD effluent, because it still contains larger amount of these COD and other nutrients. So with these biochar conditioning, then it can be used for the algae cultivation. So microalgae can serve as a second step nutrient and heavy metal removal. It is very suitable for wastewater containing less than 200 ppm of ammonia. It can use both the ammonia and nitrate nitrogen and other nutrients too. So and microalgae have often high lipid content, and sometimes could be enriched with omega-3 fatty acids. So a lot of polyunsaturated fatty acids. So it's very, very good nutrients, good feed for animals and fish and so on. And it can also be used as a biodiesel feedstock when it's contaminated, or just pyrolysis to produce fuels and so on. So this is the pilot algae production system using the AD treated animal waste for the algae cultivation. And after microalgae cultivations, the effluent still contains reasonable amount of nutrients that can support the hydroponics growth of vegetables and herbs. And so we have tested different kind of hydroponic systems, and many vegetables and herbs can grow well hydroponically. So these are again different kind of hydroponic systems, and we've also worked with these commercial urban indoor hydroponic and aquaponic systems, aquaponic production facilities and so on. So, and these manure solids and food and vegetable processing waste, restaurant waste, fish scrap and so on, they can also support this black soldier fly larva production. Therefore, treat all these waste by this black soldier fly larva. And the conversion rate is actually fairly high. About 2 pounds of this waste can produce about 1 pound of black soldier fly larva. So and then this is actually the black soldier fly larva productions, or you can also produce it by worm too. These worms and black soldier fly larvas are actually very good animal and fish feed. So Now, again, biochar can be used to condition the waters in between all these processes, and also for final water recycling and discharge. And biochar can be actually produced from biomass pyrolysis. That I will talk a little bit more later. So, and these water, of course, can then be further treated using UV, ozone, or some kind of non-thermal plasma systems for recycling or for final discharge, and So now let's look at the solid waste utilization using the microwave-assisted pyrolysis technology we have developed. We have converted these solid waste into fuels, chemicals, materials, and hydrogens, and so on, and others like biochars too. So now, of course, recycling or converting these solid waste, such as biomass and waste plastics, into energies and chemicals can be a very attractive solutions for the solid waste utilization. There are, of course, many ways to energy and chemical technology that can convert all these solid feedstock into different kind of product. And pyrolysis is actually becoming one of the most promising pathways, and it's gaining more and more interest right now, especially for some of the waste plastic utilization, for example. Now we focus on a microwave assisted pyrolysis or MAP system, mainly because microwave it's actually a very promising technique because it's actually unique advantages of these microwave heating, because one thing, it's a selective heating, so materials with different dielectric properties are heated up by microwave irradiation to different degrees, and also it's a volumetric heating, so microwave can penetrate more uniformly throughout the volume of certain material of certain size, and thus deliver energies more evenly. It can be even the inside can be even heated up faster, and then you can have this heat transfer and mass transfer go in the same direction, for example, and also it's a rapid heating, because microwave heating is an energy conversion process. It doesn't have to be limited by the heat transfer. So there's, again, a lot of advantage. Unfortunately, not all materials can absorb microwave efficiently. Therefore, we have to use these microwave absorbent to help improve the heating rate, and also improve the temperature uniformity for the pyrolysis. So over the years, we have developed many type of MAP systems, from bench top to pilot scale to commercial systems too. So so this is actually a stationary MAP systems we have developed. So again, feedstock comes in here, goes through this microwave, pyrolysis reactors, and water comes through here to be condensed to produce bio-oils, and the chars can be gasified in this bottom, stage, and then again, there's a syngas and char produced. And this is a mobile CMAP systems. It has its own syngas electricity generation systems, and it also have its own these liquid condensation systems and so on. So it doesn't rely on the outside power or water to function, and we can convert all kind of bulky biomass or any of the bulky waste plastic, those kind of low density materials on site, and bring back only the fuels, chemicals, or materials. So. And this is an improved pilot scale CMAP systems. This is actually a done draft type of system. So the material comes down here, and our waters comes out here to be catalytically formed before it actually goes through these condensations systems and so on. So and you can use these systems for all kind of feedstocks. In this case, it shows the use of sawdust, wood pellets, and so on, and chicken manures too. And this is syngas. Right now, it's fair off. Or you can use waste plastic as a feedstock too. So, and this is an example of these MAP applications in sewage sludge gasification. So this is the sewage sludge and wood pellets. So you can actually produce steady kind of syngas. And here are some pictures showing the flare of the produced syngas. So at a gasification of 800 degrees, the CMAP system actually obtain a much higher quality syngas with a low heating value of 18 megajoules per cubic meter, and about 67% volume of the syngas is hydrogen and CO, because it doesn't use this kind of carrying gas as in the case of fluidized bed, for example. So we compare with a range of other kind of gasifiers, including fluidized bed, actually outperform many of these conventional pyrolysis process. So here's the application of the CMAPs in the plastic pyrolysis. Okay, plastic waste are everywhere and polluting our environment. In fact, over 5 billion tons of plastics, which is over 80% of the plastic we have produced so far, end up in the environment as landfills or marine litters. Less than 9% is actually recycled. So these waste, plastic can be converted into valuable fuels like gasolines, diesels, jet fuels, and hydrogens, or chemicals like naphtha or light olefins and so on. Okay. So this is actually technology has actually been licensed already to a company in California for the plastic to fuels and chemicals production. But our objective is to develop a sustainable way to utilize these waste plastic to improve the financial outlook of the plastic waste recycling industry and help create a truly plastic circular economy. Therefore, the key is for the microresist pyrolysis to produce the feedstock for the new plastic production, feedstock like the naphthas or aromates and light olefins. Okay, so because they can be used to produce new plastics. So this is actually a naphtha produced from polyethylene, and the liquid yield is actually about 70%, with about in there about 52% of these C6 to C12 paraffins and 17% of these olefins, and then 14% to 4% of these C6 to C12 aromatics, and 17% of these C13 plus hydrocarbons. And then this is actually naphtha produced from a typical mixed plastic. In this case, it's 41% LDPE, 24% HDPE, and also 35% PP. And the yield is still, about 70% also. So, but those are produced in the in situ type of catalysis. In in situ catalysis, the catalyst itself and these plastic beads and so on, they are actually mixed together. Okay, so then the catalyst often experience this rapid deactivation due to some of the carbon and ash depositions, and the catalyst is very difficult to be separated from the char and ashes and so on in the downstream process for the regeneration and reutilization. So we have developed this kind of asexual kind of catalysis process. In other words, only the volatiles go through the catalytic reforming system to be reformed to produce these fuels and chemicals and so on. But in the asexual catalysis process, usually you want to have certain high surface areas, or you want small particle size. So when these kind of small particle sized particles, these kind of catalysts pack together, they create a lot of pressure drops, and also it limits these kind of heat mass transfers and so on. So actually, catalysts will actually deactivate fairly fast. So to solve these problems, we have developed these structured catalytic reactors. We use silicon carbide forms or monolith forms as catalyst support. And because they have very large void fractions, a lot of air cells, and therefore, they have, they can substantially reduce the pressure drops and still maintain the very high, surface areas, and resulting this kind of turbulent vapor flow through these foam structures is really, improved significantly of the mass and heat transfers. You pretty much don't have much of a pressure drop anymore. So these SEM images of these silicon carbide films coated with zeolite catalyst. Okay, these are under different magnifications. You can see the pore, the voids are not really, blocked at all. And you can see, under higher magnification, you can see that these zeolite coated uniformly, on the surface, and then you can see the zeolite crystals. 5 minutes left. The zeolite crystals about 1, micrometer, that kind of size. Okay, and of course, we actually compare the catalyst stability and life between these granule catalyst and the structure foam catalyst. And for the granule catalyst, after only about 150 minutes, you have a lot of wax, produced. These catalysts pretty much, deactivated already, but then using the foam structure ones, it improved, quite a bit. Of course, the catalyst itself are still the most important. So, we have used different modification protocols to fine tune the 2 key parameters affecting the catalyst life, basically the catalyst acidity and the pore structures. And of course, we don't want to affect the zeolite framework and the topologies. So this one shows that the modification of the catalyst to optimize the Bronsted acid site densities, which strongly affect the catalyst lifetime and aromatic selectivities. Only when these Bronsted acid site density are in a certain range, for example, between 0.5 to 0.9, then in this range, then zeolite can present the best performance in terms of these catalyst life. So, and this is for the pore structure modification. So for the conventional ZSM5 catalyst, the pore size is very small, actually preventing these kind of larger wax molecules from entering, these pore structures, so that limited diffusions of these intermediates and block the pore openings, so resulting very fast deactivation of the catalyst. We therefore modified these zeolite to have the hollow kind of structure, okay, and in that way you can actually create these kind of mesoporosity, and that will actually improve the catalyst life quite a bit. So I'm not going to get into the details, but basically, the conventional, the ZSM5 catalyst was dissolved and recrystallized in these tetrapyrrole ammonia hydroxide solutions to obtain these kind of hollow ZSM5 zeolite. So here you can see these are the conventional catalyst. Okay, so you have uniform kind of rectangular structure without macro pores in these crystals. Okay, and these two here, it's the D and E. It's actually after these kind of modification. Okay, so you can see all these inside larger voids around like 10 to 200 nanometers. Okay, and if you do the Fourier transform, you still see that all these Fourier transform shows. You can actually see these perfect crystal image, crystal structures after the treatment, that is basically indicating that the treatment itself did not affect the highly crystallized structure of the zeolite. And we also using the SRD patterns and so on to actually verify these two. So, and this this is the pore size distributions of the modified ones and the original ones. You can see the modified ones, the mean pore size is about 32 nanometer, while the original one is only about 3 nanometer. So the internal pore size increased dramatically, and the diffusion of molecules inside the zeolite materials is also confirmed to be much better for both two gases, and actually in the modified ones as compared to the original ones. And we actually also look at the aluminum species distribution in this ZSM5 800. So we conducted this aluminum 27 magic angle spinning the NMR experiment. The two significant peak observed in this spectrum, it's associated, at 0 and 55 ppm, it's basically associated with the these actual framework aluminum and framework aluminum species. Okay, so you can see that after the treatment, okay, the actual framework the actual framework species actually reduced, and then the in framework aluminum species actually increase. In other words, there are a lot of these aluminums actually going into these in framework structures, so they actually help improve the acidities also. So. And this is basically the actual application of these kind of modified structures. As you can see that, this without modifications, these C5 through C12 hydrocarbons, it dropped below 90% in very, very short time. But, this is for the modified ones, even after about 500 minutes, okay, still maintain around 90%. So so the catalyst life improved dramatically, okay. And this is basically the possible pathways of a plastic conversions. Basically, the plastic pyrolysis wax, easily cracked, into the long chain hydrocarbons on external weak acid side, and then they can diffuse into those micro pores of the zeolite to access these kind of strong acid site. Then they can actually go through a series of reactions to produce these naphthalene and so on. So, and we have actually verified that we can regenerate these kind of catalysts very, very efficiently. Even after 8 times regeneration, there's pretty much no changes there. And so we have applied these kind of catalysts, in the direct conversion of the waste plastic into the BTX and also light olefins. So this way we can produce these for the new plastic production easily. So, and then there's still a little bit, quickly on the uncondensable syngas there remaining, which basically the hydrogens and C1 through C4 hydrocarbons left. So we go through this kind of chemical vapor deposition process to actually produce these carbon and hydrogen materials. So our preliminary data verify the feasibility of this whole process. And then the results indicate that when these kind of non-condensable gases pass through high temperature reactors packed with different kind of catalysts, they can actually produce carbon materials and very, high selectivity of the hydrogens. And we can also deposit on these kind of carbon materials onto a nickel form or some other form like iron structures and so on. So then after this kind of, in this case, nickel is removed, dissolve away, then you can produce 3D standing, freestanding graphene forms, for example. Okay, so and then these you can see the hydrogen yield from different kind of plastic using the CMAP pyrolysis and these catalysis systems. So this HDP, HLTP, and so on, before and after, you can see the hydrogen yield. And as shown in this table.
2 minutes, is it all right?
Okay, yes, 2 minutes should be fine. Yeah, as shown in this table, again, the hydrogen selectivity can increase by 4 to 5 times, after this process. So this is basically a kind of quick energy and mass analysis. And you can see that 1 ton of plastic produce about 450 kilogram of naphtha, and then some diesels, and or some synthetic natural gas and so on. So I'm not going to go through much details, but it's and this is actually even based on the very small 1 ton per day that kind of systems that with larger scale that should improve better. So basically, in summary, there are many advanced technologies that could effectively treat solid and liquid waste through utilization, therefore helping achieve the circular economy and sustainable development, including some of the process I just mentioned. And these process, they mainly use electricity only. There's not much other kind of chemicals consumed. So and electricity, of course, can get more green and then cheaper in the near future, I hope, with all these kind of renewable energies and remote generation productions of these kind of energies. Then it certainly, these technologies could become much more practical. So that's basically, over the years, again, we actually receive a lot of support and have a lot of collaborators. I just want to thank them all here. So thank you again for your attention. So any questions?
Thank you so very much. Yes, you're getting some applause there. So this is great to see. Very impressive indeed. Thank you again. It was very interesting to see that you and your colleagues were able to develop such a variety of mobile systems, and it's very important because you can take it to the community directly rather than bringing their product. So this is very nice, and I can see there are some questions. Mr. Gao.
Hi, Professor Ran. Thank you so much for your presentation. It's quite informational with so many interesting informations. And I just have two quick questions. The first one is about, have you ever done technical and economical analysis for example, for transfer of the pig manure or the scams from the wastewater to products such as the biodiesel? So because they are quite interesting, I was wondering if they are profitable for industry application. The second one is about the biochar. So I can see you use that for the filtration for the wastewater, and I was wondering if there are any properties for the biochar, such as the pore structure or the surface chemistry, that will be specific, useful for the filtration, and also for these foam structures for the zeolites. I was very interesting. I was wondering if you ever try or use the carbon foams from the biochar that can be used also for the catalyst support, and also about these foam structures that from the biochar, from the biomass. Is that any special technology or ideas to these foam structures? Thank you so much.
Questions. Well, thank you. So first of all, the scum ones. The scum, it's basically considered, it contains a lot of oils, but those oils are heavily used. So the main issue is that these oils contains a lot of free fatty acids. Okay, so we use traditional, acid catalysis and alkaline catalysis. It's almost impossible to fully utilize these kind of free, fatty acid, because one of their products is water, and it's almost impossible to remove that at that kind of temperature. Okay, so you cannot completely utilize these kind of high free fatty acid containing oils for the biodiesel production. So we develop a glycolysis process, to actually convert them into glycerol, and then going through traditional kind of, alkaline catalysis process. Then we can use pretty much 100%. So you should, if you're interested, you should look at the publication and the patent, on that technology. And the biochar itself, we actually, produce quite a bit of biochar ourselves for a range of different applications. And you mentioned about biochar as a foam structural materials, a carrier for a catalyst, and so we also test those too. But those, is sometimes it's certainly not as stable as we like, as compared to the other like silicon carbide foams or the monolith type of the foam structure material. So yeah, thank you.
Thank you so much. Thank you.
Wonderful. Next question. Yes, there is a question. I don't see the name, but I see the.
Can I have a question?
Please, of course.
Yes.
Oh yes. Tao Zhang from Chinese Academy of Science. Thank you. Very impressive lecture, Professor Ryan. I got one question. You have mentioned the catalytic pyrolysis process. Mm-hmm. I'm wondering the in situ and the ex situ two process. So could you say more words about the stability of the catalyst? Which one is more potential commercialization from the point of your view?
Yeah, thank you, Professor Zhang. Yeah, that's a good question. So as I mentioned, the in situ catalysis process, okay, because the catalyst is actually direct contact with this raw material, so sometimes it's very easily contaminated because of the carbon deposition, because of the ash deposition, and so on. So the catalyst is easily deactivated. Okay, and it's very difficult to separate, reuse, regenerate these kind of catalysts. from ash, from the other kind of char product and so on, right? So it's very difficult to kind of use commercially. So and then in commercial there's these kind of food asbestos system with the catalyst inside and so on, but still only for some very pure chemicals. Otherwise it's not easy, especially for these waste plastic. It's not easy at all. But then these ex situ process is completely different. You actually in your pyrolysis reactor, all you do is you control the temperature uniformly. You crack these plastics into wax, okay, into wax vapors, and then only the wax vapors going out through your catalytic bed. Okay, and then now in this catalytic bed, we use this kind of foam structured kind of catalyst, and that I show you already, right? It's very stable. You can easily regenerate. We regenerate many times, but then they still performs just quite well. And even if the catalyst life is long enough, you don't have to regenerate quite often. You can after many days and then regenerate once, for example. So it depends on application, depends on raw material, depends on catalyst. But these kind of ex situ foam type of catalyst, I think that's the direction to go. So for the commercialization, that's actually in our commercial systems. That's what's being done right now. So
thank you very much.
Very much.
Thank you again. I don't see any other questions. Yes, there is one more. Please go ahead.
Hello, Professor Ron. Thank you so much for your presentation. And I'm sorry that my camera is not available. I'm a student from Nanjing Agricultural University. Sorry, can you hear me?
Yes.
So my question is concerning the microelectrolysis. I want to ask, before the microelectrolysis disposal of your food waste or sewage sludge, what kind of pre-treatments would you do, since we have to consider about the high initial moisture of this kind of materials? So I think you may involve the problems of chronic fungus before we have some
Guys.
Sorry.
We have problem.
Yeah. But I guess it's, I understand the first question is mainly on the, like those, sludge and so on, the moisture content in there, right? So yeah, I mean, moisture content is always an issue. So the good thing is microwave, if the moisture content is not too high, actually initially help concentrate the microwave, absorb the microwave, and then get heat up quickly. It's probably more efficient kind of drying using this microwave as compared to some other method, especially using like vacuum assisted, drying and so on. But yes, if there's water in there, water has to be removed, right? Before the temperature can go above 100 degrees, before they can be pyrolyzed. So, but a little bit moisture there is fine.
So
any other questions?
And that's true.
Any other questions that we have? By the way, Roger, why don't you may want to you may want to mute your mic, because we can hear when you type. Yes.